So I stopped using recording from the Google Meet. So and I'm using a screen recorder, so only my face will be recorded, not the whole. Uh, all right, so that will be our privacy kind of thing that we can manage. I guidelines and then see that this is can be done. So I'm doing that. Okay, so with that, all right. So yesterday we were the last topic. We were talking about this one, right? So we are good to go with that. And then centripetal force, and then we got the free body diagram. And the last thing that we were doing is the is this object of the plane, right? So let me draw this one more because there is a bit confusion in the drawing which I saw and what is actually there. So or I use the new one, right? Yeah. Okay. Can I please up? Sorry. Okay. All right. So today's date is 7, and so we will having a class from 7 to 8. Okay. 7 to 8. So today it might be again. It will be a little bit stretched to 8:30. Otherwise, normally it will be from okay 8 lean. And on Saturday we can do the same 2 to 3:30. Okay, cool. So let's start with date. Today's date is 07 10 2025. Okay, now let's see what was the question yesterday. The question was a 5 kg block slides down slides down a smooth incline at angle sorry. So inclined at angle 30 degree. All right. So now we have to see what forces and how we can control it. Okay. So let's see. We have a incline, right? So this will be the incline. Then let's take some block on it. Oops. Right. And this angle is 30. Now we have to calculate the overall, like the acceleration. Let's say acceleration, right? acceleration when there is no friction, right? And when we have, let's say, friction force as 10 Newton, right? Okay. Now, let's first we need to check the free body diagram, that what the force is which is acting on this system, right? So first is the weight, which is straightforward downwards, right? So this will be going to our W. Okay. Then at in first condition that there is no friction, so it will be going in this direction, right? The sliding force, the sliding force. And then we have some components which act on behalf of the weight, right? So one is the perpendicular to the slope, this one, and one is the parallel to it. Sorry, what? Perpendicular. Okay. So in a right angle triangle, right? So if this is the right angle triangle, this will be the base, this is the hypotenuse, and this is the perpendicular. Opposite of what? So yeah, so it's like the theta. In front of the theta is the opposite. It's perpendicular, right? So because this is the theta, and this theta will be the same as this angle. So this theta is going to be the this same angle. Okay. And to compensate this component, we had a normal, which is a normal force, which is opposite and equal because there is no movement upward. The block is not moving away from the inclination. Okay, so that means that should need to be that should need to be uh, equal and opposite to that particular component, which is perpendicular to the inclination. So yeah, so when it is not equal, when for example in the last example for the elevator, right, when it is moving upwards, right, so it's not equal because there is an acceleration. So where there is in the direction, if we have an acceleration, only that direction has the actual force which is moving it forward. If it is not that thing, if it is that not if that's not the case, then it should be equal to that particular component. So now we can draw a free body diagram to this. Okay, so now this is our object, right, the block. This is the parallel component, we can say parallel or PA, or almost in many books it is be shown as the parallel line. Okay, and this is our actual weight, right, and this is the perpendicular that we are talking about W perpendicular, right? So you can, in a normal ways, if there is a straight line and if we draw a line which is 90-degree to that line, it is the perpendicular. Perpendicular, right? Okay. And so now there are two components, and this is going to our theta, right? In first case, this is our first case when there is no friction, or friction is negligible, whatever it is. Okay. Now, to understand now, and then, sorry, I need to, so this is going to be our case first, no friction, right? And then there is a normal force which is equal and opposite to the force or the component which is not helping in the movement at all, right? Because there is no such movement upwards, so that should be equal. So now what we are conquering from this scenario, so first thing first, now what is given, we have given the mass 5 kg, the acceleration 4.8, the g, sorry, 9.8. Yeah, yeah, yeah. So positive and negative only plays when the weight is actually the perpendicular, actually in the plane, right? So if it is, this is Earth, and if it is going upward, or if it is going downwards. So if it is going downwards, we positive. If it is going upward, we are using negative. It's going the slide way, so only the force, so we are not considering g as an acceleration to the slope, right? We are considering g for our weight force, right? To calculate the weight, right? So because weight is also a force, so to calculate the weight, we got 5 times 9.8, which will gives us 49 Newton. So now we have our weight is equals to 49 Newton. Next thing, in this case, what will be the component, the perpendicular component will be, okay? So in every case, if it is a perpendicular, it will always be the cos, right? What it is going to be the cos theta, right? The next thing which is given, theta is 30 degree, okay? And the parallel one will be sine theta. Got it? So in this case, we have W is 49, we have cos 30, and then we have 49 sine 30, sine 30. So now you have to remember these values. Is it 1 over root 2? Can you check? Oops. Sine 30. Let me check it here. Okay. Sine 30. 1 by 2. Yeah, 1 by 2. It's not this one. And then the cos 30 equals 0.866, which is equals to root 3 equals this divided by 2. Yes. Cool. So I remember something, but not the full. And 45, is it 1 by root 2 is 45? Sine 45 equals 0.7071. Okay, just remember this number. What is 1 divided by 1.414? Yes, exactly. Right? So just for giving you some idea that what does this mean, uh, so if we have sine 30 is half, right? Sine 45 is always be 1 by root 2, right? And sine 60 is will be root 3 by 2. Okay. So in the same way, this will be cos 60. This is cos 45, and this is cos 30. So if these are the degree values. I remember. No, you don't have to remember. It's just that it's just the memory muscle that comes up. So just writing it down that these. So it's good to have these numbers handy, right? And otherwise, we need to, for a simple calculations, we have to jump over the things. All right. Okay. So mostly it will become like cos 25, then you have to take the help of calculator. But if it is straightforward, then you can have these values, right? Yes. Okay. So now we have cos 30, the perpendicular one, will be 49 into, what was the value? One, where is the calculator? Cos 60 equals 1 by 2. No, we are looking for cos 30, right? Cos 30 equals, yes, 0.866, right? So this will gives us 0.866 equals times 49, which will give us 42.4. Let's do with the 42.4. Okay, 42.4 Newton. Now for sine 30 is half, that means zero point 0.5. So 49 times zero point 0.5 will gives us 24.5 Newton. Okay. So here is the deal. In the one when there is no friction, what will be the force? Net force. Net force will be the component which is dealing, the weight component which is dealing. You getting me? So the net force, because now we are going to calculate the acceleration, and we know that F net is going to be ma, right? So what will be the, so, or we can say a equals to F net over m. So what will be the F net? Because only one component is uh, helping to move the block downwards, which is the parallel component, right? And what's the parallel component? So the total weight, the F net, is going to be, is equals to be the parallel component over m, which will gives us parallel component. Let me check. Yeah. I did again. Again, I just think that I did perpendicular and the parallel one. Yes. So the W parallel will be 24.5 over M. M is 5, which is again will gives us uh, 4.9 meter per second square. Cool. So this is the acceleration when there is no friction. Now come up to the second option. What is the second option? The friction force is of 10 Newton. Now the free body diagram got changed. Why and how? Let's see. Okay. Now we have this object. There is a parallel component, right? And there will be a opposite friction force, which is pulling it back, right? And there we have a weight component. Then we have a component which is perpendicular to it. This is the theta and this is the normal, right? Now here again, value will be same. What will be got changed? The F net. Here, F net is going to be the parallel component minus the friction, right? So the parallel was 24.5 minus 10. So F net is going to be 14.5 Newton, right? Therefore, the acceleration will be reduced to 14.5 over 5, which will gives us 2.9 meter per second square. So this is how you are going to do the free body diagram questions. You have to draw all the forces, right? And also come up with the F net thing. Where, always weight what? Not the weight is always the F net, right? Yes. So weight is this one. This is the weight. Okay, when we are inclined, so there are two components for the weight. One is the parallel one and one is the perpendicular one. If there is no friction, then the parallel one is equal to F net. That's the only condition. There is no friction, then the parallel component is equal to F net. If there is friction, then we have to calculate like this. We have to minus the friction, right? Now you got it? Cool. That's nice. Okay. The next question is hanging object in equilibrium. right? So that means there must be a tension in the hanging. So this is another type. So we have like centripetal force, and now there is a tension force which occurs while something is in tension. For example, if we have a weight of a mass, if there is a rope which is attaching to this, right? So there must be a tension force which is holding this up. It should be something look like this. Something should be looking like this. Okay. So the T is because you have also, so for someone has held it up. So there is a tension between this rope, and then there is a tension between this hinge towards the center of it. So there must be a free body diagram just like this. The tension is going upward, the weight is pulling it downwards. And in that case only, the F net is equal to be the T minus the W, the net force which is acting on it. Right? Because now there is no movement neither upward nor downwards. That means the F net needs to be zero, and therefore the tension is equals to the weight of the object. All right. Similarly, if you check to this, calculate the tension in the wire supporting a 17 kg tightrope walker shown in the figure. Right. So what is happening here is the rope is now bended 5 degree. Can you see that? So now there are like TL, TL. So this is the tension right. This is sorry, tension left. This is tension right, and this is the weight, right? And this is the free body diagram. Now there will be one component which is let's see here. So now there will be two forces which is acting. One is the tension left one, and then there is a tension right one. We will do this question to just to make you better understanding of tension, because I in the examples I do have only one, but this will be seem interesting. We will take this as an example and then we will see how it goes. Okay. For what? Okay, what is the tension? So what is the tension? Tension is another form of force. Newton. Right. So we are talking about forces, different types of forces, which acting on a acting on an object. That means it need to be a Newton. Okay. All right. So let's see. First, we will take some a simple example: hanging of a mass. It's a simple one. Uh, then there is the weight. So there is a T force which is acting like this up, because there we have like the hand which is holding. So there is a tension between the rope and the hand, and there is a tension between the weight and the rope itself. They are both canceling each other, but there is because it's not moving. That means the T, the F net, or we can say in this case the F net. What I'm writing, F net is going to be T minus W because of the direction. If I draw a free body diagram, the T is acting upwards and the weight is acting downwards. So just the opposite direction, we are using T minus W. But because F net is equals to zero, why? There is no acceleration, baby. right? Always remember, if there is no, why is Fnet 0? Because there is no acceleration. That means straightforward. Okay, acceleration. There is no acceleration. So that means the tension minus W equal to 0. That means the tension is equals to W, right? The weight, and we know the weight is T equals mg. So this is the way we are doing the calculation of the tension in a rope. Okay, from here, let's take that example. I am putting this as if a topic which says hanging object hanging object in equilibrium. Okay, so now equilibrium itself says that nothing is happening. There is no such movement in both the sides or up and down, right? So in that case we can say F net is 0. Cool. Yeah. In equilibrium we must say F net is 0. Now, taking that example of hanging mass, that's good. Okay. Okay. One more thing before doing the complex one. One more thing that we need to do before moving forward. Let's do one example related to the centripetal force. Okay. Car turning in a circle. Okay. Now the topic is car turning, or let's say car on a flat road turning in a circle, right? The question says, the question says a 1200 kg car moves at 15 meter per second around a curve of radius 30 meter, right? So what is happening here? What is happening here? Yes. So something like this, if there is a path, let's trying to draw, right? This is the radius, 30 meter. Mm, I don't know how to draw a car, but let's say it is a car, right? It's look okay. Now, so this is the object now, which is moving in a circular motion, right? So let's see how we are going to see our forces. Okay. So one, there is, for example, if this is the object, it's not moving upwards. It's So it's on the floor. That means the weight is equal to the normal, right? But there is another force which is pulling it, it's moving it towards the center, but on the inner speed, right? Which is the centripetal force, which is the centripetal force, right? So now we have to see that what the all weights are, right? So the first, what is given? The mass, 1200 kg, the radius, uh, 30 meter, the velocity 15 meter per second. Okay, the value of g, which we know, 9.8 meter per second square, right? Now, considering this, we know that the weight will be mg, which is 1200 times 9.8 equals 11760 Newton, right? Therefore, the normal force should be equal to the weight, right? Which is again equals to 11760 Newton. Why? Uh, we must say balanced vertically. In the balance, in the vertical motion sense. But you catch the word. That's nice thing. Okay. Yeah, that's good. So vertically they are equilibrium because there is no such movement. The car is not lifting upward and going beyond the road, right? It's just that because it's balanced vertically, that means the force which is pulling downwards, and there should be an equal and opposite force which is called normal. So that's the main thing. But then because it is in the radius, there is a force which is pulling it towards the center, and there must be an equal and opposite which is creating, because it's staying on the road, it's not going off the road, means we have to see the centripetal force, right? So now we know that fc equals m v square over r, right? M is given 1200, r is 30 times v square. Do you remember 15 square? No. Oh, nice. Or you're using calculator. Okay. 40 into 2025 equals 0, 0, 0, uh, then 8 and 1. I think 9,000 Newton, right? Okay. Now my muscle memory says that I should let you know the squares, right? So 1 square, 1, 2 square, 4, 3 square, 9, 4 square, 16, 5 square, 25, 6 square, 36, 49, 8 square, 64, 9 square, 81, 10 square, 100, 11, 121, 12, 144, 13, 169, 14, 196, 15, 225, 16, 256, 17 to 89, 18, 364, 364, 389, 381, sorry, and then 400, right? So these are the squares. I personally ask my students to learn these things, these values, just to because we are dealing with mathematics and physics, right? So it's required basic. So for example, if you have to race in like 100-meter sprint, you have a different training than if you want to race in a marathon, right? You have to train your muscle differently for a 100-meter race, but the common thing is the stamina. You have to be full of stamina and strength. You are opting a career which requires much more advanced calculations and advanced formulas, right? So these are the least basic things that we can trigger to remember things, right? Mathematically, which is pretty much important, which helps you derive your brains. It takes away from your journal chores to give a sense of uh, a discipline, you can say, to your neurons, so that there is no such distraction while doing these kind of exercises. So this is a smart way to exercise your brain muscles. All right. Yeah. So this, the squares, anything, any value. For example, in our in physics, there are lots of constants which need to be remembered, just like G 9.8, and pi 3.14. Do you get any like, if you force, you don't need to force yourself to remember the value of pi, because you know it is 3.14, because you are learning, or you have a childhood memory, right? I believe you're still a child, but still, a long time you have just remembered that value. It's still stuck, because that's the only value you are playing over and over time. So that's the general practice to remember things. We should not sit in one sit and trying to remember. Do it daily. Write it down once daily, and you will see over like 2 3 weeks you will learn by them heart these values. All right. So the centripetal force is 9,000. The normal weight is this, and the actual weight, which is going to be like that. So that's how we have to deal with, and we can remembering the arrows, right? So in this single topic we have covered like our free body diagram, the forces, all the forces that we are talking about, right? The tension, the centripetal force, the force for the linear motion, the projectile, whatever it is. All right. Okay. uh, Now let's do one that example, and we will finish this class today, and then tomorrow we are going to do some questions which is being asked in past question papers, right? One, two, three. For the impulse and collisions, right, with the wall, I have put it in a manner. Then, when there a question comes up, I will explain the whole theory in that. Okay. So it's like it will a small part, but still there. And then we'll start with work, power, energy thing, and how we can use those values to solve the example. Yes, work power energy will be the maybe the last, and then 1 hour thing for spring and hooks, right? I believe that you are parallelly doing your skypad, so if you have, so do whatever you can do, right? As your father also saying that there are other subjects that you need to practice, but at least give like 1 hour, accept my tuition, so 1 hour will be definite. So go through with, if even if you know that these are the answers, just go through with those questions which you think you can attempt it, and try to attempt those and solve them. Don't worry about the correct answer or the wrong answer, just try to attempt them. Number will be remain same. I'm repeating over and over again with the same intensity, because that's the only way that we can get at least achieve or merit in our questions, right? Okay. Okay. Mm, okay, that's the cleanup. Okay, now come with this one. uh, Let me draw this one first. Okay. Let's see why how it is goes. Okay, a bit complex. If you think that it is more than your like these type of question never been have asked, let me know. We will not do it, but just think about it in your free time, right? This is the pole. This is the dotted line, and then there is a curve. I'm making it a bit, oops, bit more, right? And then now we know that there will be a tension which is moving towards the right. There is a tension which is moving towards up, and then there is a weight which is pulling downwards. Okay. Now, and then there is an angle of 5 degree, angle of 5 this side, and it should be the same from this side. It's that means it is in the middle. Okay. Yeah, so that the person who is standing is in the weight. What else is given? So now they are asking, calculate the tension in the wire supporting the 70 kg tightrope walker shown in the figure. We have to calculate the tension in the rope, right? Calculate tension in rope supporting the 70 kg tightrope walker. Interestingly, they have just draw the diagram, and then they haven't given much information regarding that. We are just assuming, right, or according to the diagram which is given. Okay, so what is given now? We have the mass of 70 kg. The angle is 5 degree. Then we have g, which is 8 meter per second square. Okay, now let's make the first step to solve this. What is given? What has been asked? So that's the tension T. Tension T. Another form of the what we can say, the force, right? So now they are not asking for anything, the acceleration or anything, because there is no such acceleration up and down or sideways. He's just standing there, balancing it by himself, right? So as you can see, the figure in the wire is not perfectly horizontal. It cannot be, but is bent under the person's weight. Thus, the tension on either side of the person has an upward component that can support this weight, right? Now, as usual, forces are vector represented pictorially by arrows having the same direction as the forces and lengths proportional to their magnitude. The system is the tightrope walker, and the only external force acting on him is weight and the two tensions, tension left, tension right. Right? It is reasonable to neglect the weight of the wire itself. The net external force is zero since the system is stationary. Why the weight or Fnet is zero in the previous one? Because the system is stationary. There is no movement. It is in equilibrium. The word that we have used, and we can also say the system is stationary. There is no. So the net force, net external force is zero. Right. The second thing that we can write it down is net external force is zero. That means F net equals to 0. So now that's the second equation, right? Trigonometry can now be used to find the tensions. One conclusion is possible at the outset. We can see from part B of the figure that the magnitudes of the tension TL and TR must be equal. You can see, right, the magnitude of, because it's not like in the other side, so it is always be same in any point of the time. It will always be the same, right? So the magnitude, the second thing that we can say, magnitude of TL and TR are equal. That's the thing that we can conquer, because there is no horizontal acceleration in the rope, and the only forces acting on the left and the right are TL and TR. Thus, the magnitude of those forces must be equal so that they cancel each other out. Why we are saying? Because there is no horizontal movement. That's why TL equals TR. To show the magnitude, we use the modus operator. I'm just using TL equals to TR. Okay. Okay. Whenever we have two-dimensional vector problem in which no two vectors are parallel, the easiest method of solution is to pick a convenient coordinate system and project the vector into axis. In this case, the best coordinate system that we can use is the horizontal and the horizontal and vertical. We call the horizontal axis x-axis, so it's just giving the all over the sense that we are talking about. Okay. All right. Now this is where the actual things comes out. So let's say we know what is being here. So what in the both senses I'm taking the same nomenclature that has been using over here. Okay. So how in the left hand side, so this is our left hand side. Okay. So I'm trying to do similar thing so that you can derive like that. Okay. Now there is this, and now there is this. So this is our TLY component, right? Sorry, totally mismatch. So this component, when I'm talking about, this is the actual tension, TL, right? This is our the TX one, TLX you can say, TLX, right? They have used, because there is a uh, L component, because this is the theta degree, right? The 5-degree angle. This is, so there is a formula, there is a way where we can take this whole vector toward this one, right? So that will be our TLY vector, the Y component. So remember there are X axis and Y axis, and if there is a straight line, we can use like this. So this is our Y component, which is equivalent to here, right? So similarly, if I draw the right hand side, right? This is the theta. This is our TR component. This is our TRY component. This is our TRX component, right? Now, let's draw our final free body diagram. Okay. Alrighty. Now we know downward there will be the weight component, right? Okay. The second thing is we can conclude here is TL is equal to TR. Also, we can say the F net X equals to 0 and F net Y equals to 0. Why? Because there is no such movement nor in the X direction, horizontal direction, not only in the horizontal direction but also in the vertical direction. There is no such movement. So both the components for X and Y, they are 0. The system is in stationary position. There is an equilibrium. That's why it is need to be considered as this. Okay. Now, so this is our x-axis. This is our x-axis. This is our y-axis, right? So in y, we have TLY component. We also have TRY component. I can show you. Let's do what's here. You can see this one. So if I'm saying, let's say here, right? So now, if I'm saying that because remember that we have in our inclined example, what we did is there are two. Now there are two like this. This is tension left. This is tension right, and this is the weight, right? So now, because of the angle, there are components which is acting this side and this side, right? Yeah. So this is the TLX1 and this is TRX on this plane, right? And which is perpendicular. So that's also the TLY component and TRY component of this arrow. Yeah. So that's the upward. That's true. Both are the ups. The Y component is on the both on the upside, and the X component they are opposite. Sorry, X is like, yeah. The X component is like the parallel of this thing. No. It's horizontal only. Okay. So now X component is horizontal and Y component is vertical, right? So that's how we are dealing with this currently. Okay. Similarly, I have drawn these things. So these are the Y component, which is very vertical, and these are the X component, which I'm writing it right now. TR X component, TR TL X component. Okay. Now, from here we know. Now there are a couple of questions that we have written. The Fnet is equal to 0 because Fnet X is 0, Fnet Y is also 0, right? Right. So now this is where we have to think about as of uh, a little bit of trigonometrical operations which is being used to solve TL and TR. Okay, TL and TR. Okay, now we know that from, if I'm saying f net x equal to 0, that means the TLX equals to TRX because they are canceling each other, right? The x component, they are opposite and they are equal. That's why there is no such horizontal movement, right? So this is one equation. We know we know that cos theta, right? Now, from our knowledge, we know that cos theta is equals to base over hypotenuse, right? Remember that? The base adjacent, yeah. Okay. Adjacent and perpendicular, right? So the one is adjacent and one is perpendicular. So the cos theta is adjacent over base. I'm just mentioning a normal right angle triangle. If this is theta, right? This is 90-degree. So this is going to be the adjacent. This is the perpendicular one, and this is our hypotenuse. Cos theta says base or axis over hypotenuse. Similarly, now we can use the same uh, information over here. We know cos theta, so the cos theta will be cos 5 degree, right? Is equals to base. Now, where this comes from this diagram, right? So we know that this is our diagram, and we can say from this TL and TX. So this TL and TLX, right? So this is one thing. Similarly, we can say, okay, it's just proving that. Similarly, if I'm saying Rx, so cos theta, cos 5, cos 5 is also equals to TRX over TR, right? In this way, what we concur is TL. That's what we have predicted previously. TL equals to TR, which is equivalent to the total tension, right? Now, now we have to consider the vertical one. This is quite interesting. So this is quite interesting where we have actual values. We know what will be the Fnet then in horizontal way. I'm using Y for horizontal, okay? That will be TLY, right? Plus TRY, which is minus W. Y minus W because W is in the downside. Both TLY and TRY are the upside. So the net is going to be, and we know that F net Y equal to 0. So that's why TLY plus TRY minus W equal to 0. That means W equals to TLY plus TRY. This is what we conquer. Sorry? Yeah, we will come to that number point as well. Right? Yeah. This is a one whole, so much. Yeah. So now, what is going to be our uh, TLY and TRY? Right now, because they are they TLY is equals to, let's first we know what we know is, because for the vertical component we know that the sine theta is equals to the perpendicular over hypotenuse, right? Here the perpendicular is the TLY, hypotenuse is our TL, right? Therefore, TLY equals to TL times sine theta. Theta is 5 degree. Cool. Okay. And TRY, similarly, TRY will be TR sine 5 degree, right? We know from the above that TL equals to TR, right? We know that TL equals TR equals T. So now these values 1, 2, 1, 2, using these three, using 1, 2, 3 in, let's say, I. Okay, in I. What we are getting? Uh, W equals TLY, that is this one, right? So I'm replacing, so let's say first I'm writing TLY sine theta, sine 5 degree, plus TR, TR sine theta or sine 5 degree. Now W equals TL, I can write instead of TL, I can write T sine 5 degree, plus I can write T sine 5 degree, right? Which gives us 2, which will gives us T 2T sine 5 degree, right? Now here we can say W equals 2 sine 5 degree, right? Now here comes the thing that we are, the question was to calculate the tension. So now the tension is our subject, right? So the T equals, or if in the mere 2T sine 5 is equals to W. Now T is equals to W over 2 sine 5 degree. Okay. Now we know W is mg over 2 sine 5 degree. Can you tell me the value of 5 degree sine 5? M is 70 sine 5 degree. Okay. For 0.0872. Okay. 70 into 9.8 over 2 times 0.0872. So that's why T equals, what is given? 3900 Newton. This is how you are going to calculate. This is the most critical, you can say, the question can be asked in your question paper is something like that. It should have not that much complex, but it should have to, you will make you to, it will make you to calculate the sign values, the sign with comparing with our normal trigonometry, the sine cos values, right? So the key point here is what you need to be taking care of it is this. Let's go upward. In these type of questions, TL equals to TR. In the stationary, Fnet X is equals to Fnet Y equals to 0, right? And the we know the values, but we should remember this thing as well. Okay? If you do these things, remember these things, then you are good to go. I know. I'm just giving you an example, the most critical example, that if it is asked, you still have some knowledge to solve it. If you can go through by heart, right? It will definitely will be a game changer in your learning experience. But overall, even though it's pretty much critical, but still has some basic formulas that you have to remember, that what is the cos theta is, right? What is the sine theta is, and rest of, if you draw this thing, if you draw this, that will enable you to solve the most of the examples. Okay, if you are able to draw free body diagram, you can try. I have asked you to try with your force questions thing, to go and solve, or not solve, at least draw some free body diagrams and see how it goes. Yeah, you will have a clear picture where it is like give you that what need to be calculated and what time we will going to calculate. As if on the slope thing, we definitely able to get the, okay, there is only one acceleration, we need to get the parallel component, which is going to be the w parallel, which is the sine theta one, right? So uh, it's too complicated for you at this moment. Okay, I will send you. It's Let me send this. Uh, or Google. Just a second, please. Oops. Okay, here. This chat. Okay. It's pretty much like everything I have. I'm doing with my all my students, not only going through with the small topics that has been given in your revision notebook, but also with these books. It will definitely going to help you understanding more complex situations. Go through with it. If you find anything much complex, leave it as it is. We will do it in our next classes after the exam if you want to continue. Okay, your 13 experience, but at least you have something to learn about. Okay, all right. You just click on it, but I'm not sure if our call will end. It will end up that way. Okay, you sorry. All right, good. All right. From tomorrow, I will try to cover much more than going through with much complex things. So let's complete first what is being left, and then we will do some questions. Okay. Tomorrow, not tomorrow. On Saturday, I will try to cover up. It will be like need to be going to like 2 hours class. So I will cover up all the rest of the topics. Then we will do our questions. Okay. Good. Okay. See you on Saturday. Enjoy your learning. Bye.